And I actually built this prototype. Obviously, it's much smaller, so it's made out of 3D parts. But first, I'd like to explain a little bit about Nikola Tesla. He was a physicist from 1856 to 1943, and he was a Serbian-American inventor, or just an American inventor. He immigrated to America in 1884, where he was employed by the Edison Machine Works. That's where he became naturalized citizen in America. And he actually invented lots of stuff, things that we'll go over that in a minute. However, this is where he became licensed also by Westinghouse, and where he was employed later on in 1888. Unfortunately for Nikola Tesla, a lot of his designs went unnoticed and were kind of shoved off by mainstream things, because during the revolution, the Industrial Revolution, they were just inventing things and finding these new technologies. This turbine was actually one of those, and it's supposed to be an extremely efficient turbine. Some of the things that Nikola Tesla invented were the induction motor, and what it runs on is a three-phase alternating current. I think we're all familiar with that. We wouldn't have anything in our house if it wasn't for three-phase alternating current. And he also invented a one-way valve that's open on both sides, but the flow actually stops the flow, even though it's open on both ends, which I thought was really interesting. He's also a pioneer of X-ray photography. He's not the pioneer of it, but he invented some of the things that we want to know, including three-phase. So his original idea was that this turbine would be successful in harnessing the geothermal energy due to its high efficiency. And he projected that the efficiency rates would be closer to like 95%. However, it's later been tested that they're closer to 54%, but in general speaking terms, that is actually extremely efficient. Most standard turbines today run between 21 and 32% efficiency, and in a power plant situation, that is a lot less efficient than 54%. Some of the general designs of this prototype, what it runs on is it exhausts through the holes here. You can see there's little small holes here in front and on both sides. The air comes into the inlet, which is here. In a geothermal application, this would be tubes directly connected to a source of liquid power, or actually air, steam. It could be anything. It can actually generate as a pump or as a turbine, which is very interesting. What it works on is adhesion and laminar flow, which a lot of traditional turbines actually run on turbulent flow, which is far different than what this design does. What adhesion is when the air molecules land on top of the disk, they actually try to flow towards the inside through centripetal force of the disk spinning. They're impelled, and the molecules are sent towards the center of the disk. A lot of us feel this on roller coaster rides. However, what's different is the laminar flow quality that it has. So the air molecules or the water molecules, whatever molecule it is actually just taking like a short ride to the center, basically. But it's the fact that there's less friction on the blades that actually creates some of the efficiency that it has. So what sets it apart from other turbines is the ability to pump fluid with any temperature. So it's a very high efficiency in that way. It has the ability to use lower quality fluids, so you could pump things with less water quality into it and air quality, and it would be more efficient in that way, which saves a lot of money because you don't want to filter water because it costs money to filter water in a power plant situation. Also, you could eliminate the need for a gas phase separator. So if it was a primary tool, it would eliminate the need for some of the temperature phases inside of the tank, where it mixes between the condensate and the gas. It would actually eliminate that whole phase, which if you look at that on the next slide, you can see that a general turbine, that the phase separator losses are close to 40%. So for this particular type of turbine, I'm not actually sure what the conventional turbine they're speaking of was, so that's hypothetical. I don't know what the system was because there's many types of systems. they're saying in this case, it's actually 19.6%. So the phase separator losses account for 40% of that total system. And the net energy for sale was only 19.6 in a typical turbine. So the first thing I had to think of was how I was going to reproduce this in a smaller version, and where would I find the materials? The first problem I had was I couldn't find for Schedule 40 PVC pipe that would fit my CDs, because that's actually what it's made out of, are CDs inside that have been modified. I also wanted to make it cheap enough so that you could use it as a presentation of what this type of turbine does. So it's made out of CDs and 3D printed parts. So the next problem I had to solve was I had to find the missing pieces that I didn't have on hand. So I created the 3D printed parts, and I actually went to Home Depot and I bought a few, what are my flanges? They're just little bolts, and I found some miscellaneous pieces that were a tie strap. Here. So this is kind of the idea tree that I had for my bladeless turbine. I realized that I had a control, which was the pressure system, and that I would have to supply a certain amount of pressure through an air compressor. So my air compressor had to be able to go up to a higher pressure gradient. So I had to find a really efficient compressor, which I did. I had a 150 PSI compressor. Some of the measuring devices I would use were pressure gauges on a compressor, and I needed a pressure gauge that I could control the pressure inlet and outlet so I could take my data. Or the one added thing I added to my prototype was I actually wanted to generate some sort of power. So I wanted to see the 3 phase that I created. And I did this by putting coils along the outside, which it's not very effective. It was more of an afterthought, I think, where I placed the coils. So my 3 phase isn't exact, but it does show 3 phase. So here's my compressor. And you can see it's 150 PSI. So my discs were, for my bladeless system actually, was CD-ROMs, and they were 5 holes, 72 degrees apart, and they were 5 plunge cuts. And I just did that with a regular drill. But they had to be perfectly in line with the case on the outside, because that's how the exhaust works. The airflow goes into the top, and it is evenly spread throughout, so that the molecules can spread evenly along the disc. The good thing about using CD-ROMs was that the rotational speed is already pre-balanced, and it's already 100 or 1500 RPMs is what they're rated for. So that was good. My bearings, I just took off a pair of skates that I had at the house, and they were Swiss skate bearings, so they were really efficient ceramic bearings. I tried some other bearings, but I didn't like the outcome. So it's really, you can see the mechanical relationship there. Cheap bearings do not help you with anything. So here's what the blades look like inside. So it's just a series of CDs inside. This is really it. This is everything. And that's my Maybelline. That's what I found to fit through the holes that would line everything up perfectly. And these are the neodymium magnets, or I always say that wrong, neodymium magnets. And they are the flat circular type, and I went online and I could see to check out where the lines of flux would be, because that's where I was going to get the most alternating current out of them. And I placed them negative, positive, so that I could get right next to each other along the front. They go, oops, I went backwards. The top one. Okay, negative, positive, all the way around, just like that, and there's 6 there. But what was cool about placing the CDs in this fashion, or the magnets in this fashion, was that I got a larger range of flux around the outside, so I could, where I wanted to place the coils, that was good for that, because I got more flux on the outside. Because my power was my electricity would be directly proportional to the amount of coils I had and the lines of flux. So I went on and used a calculator there. The case itself was built in SolidWorks. I don't have any of the technical data up here, but this is how I built the case. And here's my three-phase system. It is not exactly a three-phase system, just because of the orientation of where they're placed on the outside. If I'd redone it again, one of the things I would have changed was to place them closer together and have definitely more turns, because it's alternating current, you need a lot of turns. And some of I must have miscounted on a few, because one of the sides was slightly larger than the other. This is actually a map of the whole thing. And right now it's operating at about 110 PSI. And that's off of an oscilloscope. Okay. So two of the calculations I took were the pressure to RPM, and the RPM to voltage values. And you can see that with the change in pressure, you get a large change in RPM, and you also get an exponential value of a change in millivolts per phase. And I was limited by my compressor beyond this point from 90 to 130 PSI. And then for the CDs, I was limited at 1500 RPM, but I couldn't get my compressor to go any higher than that. And then for the coils on the electrical side, I was limited by the number of turns. So if I wanted to do a better system, I would have added more turns. So one of the applications this would have worked at. So to sum it up, the applications for this would be best as a primary generator, and to use maybe a typical system in series with it, or you could take multiple of this type of generator and put them, they're actually extremely efficient among each other as well in series or in parallel, and you could use the efficiencies for redundancy purposes. It's less costly to make them, they're a very simple design. I mean, there's really not much to them, made it with CDs, and they're very easily maintained. So these are why we're excited. And this is actually a very interesting article. If anybody's interested, I can pull it up for them. And it's about this organization who actually makes these, because they're not commercially used right now. Any questions? Oh, in the back.
So nobody's using them commercially right now? Do I have somebody ever use them?
No, the application hasn't been used. These fellows here in the Tesla engine organization, they've actually done one design where they tested it. That's where I got a lot of this information from about the efficiencies, because they've actually done a really large scale one made out of steel, and they've actually applied it in a geothermal application and done some tests. And so that's where a lot of the efficiencies came from. But as far as commercial use, they're not used right now. Any other questions? In the back?
Where were the bearings? Were they in the circle of the...
Oh, sure, yeah, you can go back, I'll show you. Okay. In the center there, I just placed them, I made them, the great thing about using SolidWorks is I can make everything nominal on the inside. So the bearings are at a tight fit in the center. So they actually were being held inside there by this little area here. So they're just a simple skate bearing. There's nothing special really about them. They were just off of a pair of roller skates. So that's basic design. I just wanted to be able to make a prototype of it. That was very interesting. Very interesting. Little turbine. Any other questions? Eddie, in the back.
Yeah, what is a CD?
A compact disc. A compact disc. Had to go there. And that is all. Had to be somebody. Always good.